How Does the Sun Produce Energy in the Form of Heat and Light by Jennifer Finlayson. There is a reason why our planet Earth can live and thrive and is the only place in our solar system that can do this. However, scientists think that microbial or aquatic life could be found in the methane lakes of Titan, on Europa, or on Enceladus. As of right this very moment, our planet is the only one that can support life. One of the main reasons that this is possible is that our planet sits within the Sun's habitable zone, which also goes by the Goldilocks zone. Earth sits in the perfect spot that is not too close nor too far from the Sun and its energy, light, and heat, which is needed for all chemical reactions to occur. Can you imagine what life on Earth would be like without our Sun? The honest answer is that it would suck. Earth would become much colder without the heat our Sun provides, and the oceans would freeze. Our food supply would also become scarce as time goes by because plants can't grow without the sunlight they need for photosynthesis. Our weather is also powered by the Sun's energy from evaporation in the water cycle. We can't be sure how it would be if our Sun didn't exist anymore, but life on Earth would not last long is certain. We use the energy of the Sun in so many ways. Have you ever wondered how the Sun makes all the energy that it produces? Let's take a look starting with the nebula theory. Scientists can explain this activity of stellar energy generation by looking back at how the formation of stars begins, which is called the nebula theory. According to Futurism.com, this theory states that the nuclear reaction inside of a star began when a vast cloud of gas and particle known as a nebula collapsed under the pressure of its own gravity, and it is this collapse that ultimately birthed the big ball of light in the middle of our solar system, as it triggered a process where hydrogen atoms began fusing together due to the excess of pressure and heat to create solar energy. The nuclear reaction, fusion, that happens in the Sun's core is where the process of producing energy begins. This sunlight looks white, but it actually contains all the colors in the rainbow. Let's check out how the Sun makes its energy. The Sun consists primarily of 75% of hydrogen gas and 25% of helium gas. Not like Earth, which consists of iron, many kinds of elements, rock, and water. It is the largest object in the solar system. It is thought to be around 4.5 billion years old and will probably be around for another 5 billion years. Both the Earth and the Sun each have a core, which is the hottest part of their many layers. The Sun and the stars that make up our universe can generate energy because they are giant balls of fusion reactions. The surface of the Sun is about 6,000 Kelvin. All the solar heat and light that the Sun produces is more than enough to produce daylight and keep it warm, so that life can continue here on Earth. Besides the heat and light that is produced, the Sun also produces streams of charged particles that are known as solar winds. The Sun's core is so hot, about 15.7 million K, that the hydrogen atoms inside the core are squeezed tightly together and heated to the point where they fuse themselves together. Besides the Sun's amazing amounts of heat, there is a huge amount of pressure in the Sun's core as well. This reaction in the Sun's core is called nuclear fusion, which creates heat and light photons and where atomic nuclei join. This nuclear fusion is close to what a hydrogen bomb explosion produces, just on a much bigger, more powerful scale. This reaction converts hydrogen atoms into helium molecules, and the byproduct of this reaction in the core is a vast amount of energy that is expelled outwards from the Sun into the solar system. In a single second, our Sun will fuse together around 620 million metric tons of the hydrogen found in its core. This is enough energy that the Sun makes in 1 second to make enough energy to power New York City for somewhere around 100 years. The bigger the stars, the more pressure and heat they have, which means they are able to fuse together heavier elements. When heavier elements are fused together, there's a lot more matter that is non-conservable, which allows more heat and pressure to be generated. Have you ever wondered why our Sun above us has not exploded yet? The fusion reactions in the core, which produces an outward type of pressure, gets balanced out by an inward type of pressure that is created by a gravitational form of force made from all the other gases that surround the sun's core. When a fusion reaction in the cores of some stars find themselves becoming very weak or too strong, they can and have exploded or collapsed on themselves. So it could happen. Thankfully, our sun's pressure, both outward and inward, are very balanced, which is why we have so much of the sun's energy flowing to us. If gravity was stronger than pressure, the sun would shrink. If pressure was stronger than gravity, the sun would grow. The Earth only receives about an estimated 2/100000th of all the total energy the sun makes, and in that amount, a third of that energy goes back into space because Earth's clouds and snow reflect it. There's so much energy released from the sun in the form of light and heat generated from the nuclear fusion process. Each of the sun's internal layers play a part in making sure that all of the solar energy gets parceled out for enough to keep life on our planet maintained. Most of the energy, about 99%, produced by our sun is formed inside the core. The core of the sun extends from its center to 20 to 25% of its solar radius. It results into the fusion of 4 hydrogen molecule protons into an alpha particle, which is 2 protons and 2 neutrons that are held together as a particle, which is identical to a helium nucleus. The 2 protons combine to form a deuterium nucleus in the beginning, which is made up of 1 proton and 1 neutron. An excited photon is produced that has a wavelength in the gamma ray part of the electromagnetic spectrum. There are 2 positrons that get released, along with 2 neutrinos, and those neutrinos charge the 2 protons into neutrons and energy. Each deuterium nucleus will mix with another proton, forming a helium-3 nucleus. In the end, 2 helium-3 nuclei combine to form a helium-4 nucleus, consisting of 2 protons and 2 neutrons. The 2 protons, which are just normal hydrogen nuclei, are released and can be used in another fusion reaction. The helium-4 atom is much lighter than the 4 hydrogen atoms that began the process to make it. So where's the rest of the mass? This is where the massive amount of energy is created, given off by the nuclear fusion. 2 helium-3 atoms fuse together, free a neutron, and releases 17.59 mega electron volts, called kinetic energy, and the corresponding amount of the mass goes away because the mass is converted to energy. In Einstein's formula, E equals mc squared, which means mass can be converted into energy. The fusion created in the core stops by about 30% of the sun's radius. According to Universe Today, the sun releases energy at a mass energy conversion rate of 4.26 million metric tons per second, which produces the equivalent of 38,460 septillion watts per second, and equivalent to 1,820,000,000 Tasar bombs, which are the most powerful thermonuclear bombs ever built. After this layer, most of the fusion process will have almost stopped. Then the sun gets heated by the flowing energy that comes from the core and moves through all the different layers, finally reaching its outer layer and letting go into space as either particle energy or sunlight. There are different layers to the sun, which include the radiative zone, the convective zone, the chromosphere, the photosphere, and the corona. The radiative zone is a layer immediately next to the core and has no thermal convection, but solar material that is hot and dense keep the thermal radiation transferring heat outward. The temperature in this layer drops from 7 million Kelvin to 2 million Kelvin. The density is also less in this layer. The convective zone is the sun's outer layer, which includes everything beyond 70% of the inner layers. The temperature is lower, and the heavier atoms are not fully ionized, which doesn't make as much heat. The plasma helps convective currents to happen, which helps rising thermal cells to allow heat to escape the sun's photosphere. Some of these cells sink below the photosphere, where they cool Their density increases, and then they sink to the convection zone where they get more heat. The turbulent convection in this layer causes a magnetic north and a magnetic south pole to be produced on the surface of the sun. Sunspots happen on the surface that correspond to the magnetic flux and encourages more convection. The chromosphere is the next layer of the sun. This layer is superheated because hydrogen burns in this layer. Therefore, this layer emits a reddish glow, which is only visible during a solar eclipse. The chromosphere plays a role in the conduction of heat from its interior layers and projects it outwards. The photosphere is the surface of our sun that is visible. This is where the sunlight and heat are radiated into space. It is also the layer where the energy of the sun is released as light. This light reaches our planet in 8 minutes due to the distance from our sun to the Earth. The upper portion of the photosphere is cooler, which means the sun appears brighter in the center than on the outside. The farther away from the core that these layers are, they get cooler since there are no more fusion reactions occurring in these layers. However, they help to progress the heat and energy that is produced away from its core and into space. It has bubbling granules of plasma, which are bright, and cooler, darker sunspots which move around the sun. The sun is a giant ball of gas and rotates on its axis at different rates. This layer is a source of solar flares that produces X-rays, ultraviolet and electromagnetic radiation, and radio waves, which extend above the sun hundreds of thousands of miles. On the left is a picture of a solar flare, and on the right is a picture of sunspots. The corona can only be seen during a solar eclipse. It looks like streamers of ionized gas that go into space. The temperature of the corona is 3.5 million degrees Fahrenheit. Solar winds form as the result of the cooling gases. The corona is hotter than the photosphere, which makes no sense since it is further away from the core. A few possibilities as to why this might happen are because of the giant super tornadoes and nanoflares. As the heat and energy travel closer and reaches Earth, our ozone layer in the upper atmosphere helps to filter out most of the sun's ultraviolet radiation, letting some escape through. It is then absorbed by the Earth's air and crust and is the energy that is mandatory for all life on Earth to survive. The solar constant, according to worldbuilders.org, states that the solar constant is the amount of solar energy per square meter that reaches the Earth's surface at the equator at noon. As stated before, the Earth only receives about 2 billionths of the energy produced by the sun, and that is quite a lot. Photosynthesis only uses about 0.023% of this energy that reaches the surface. Part of the sun's energy is reflected back into space, and the reflective quality of a planet is known as its albedo. The amount of energy that is required to warm the land and water is about 42%, and the warmth of the water is actually being radiated back into space, but the sun's energy replenishes this warmth. The Earth's water cycle, the evaporation, the precipitation, all uses about 23% of the sun's solar energy. Our winds and the currents in our oceans use about 1%. The need for the sun's heat and light are mandatory to survive, because without it, everything on our planet will die. We must maintain a cleaner, greener, happy Earth and pray that our sun lasts a very, very long time. It's the Works Cited page with all the sources listed.